Hello everyone. Think about the hands of a clock. They sweep around, but always about the same central axis. That's a perfect example of rotational motion about a fixed axis. To describe this, we introduce angular displacement. If a particle moves from angle theta sub 0 to theta, the displacement is delta theta, equal to theta minus theta sub 0. This single variable describes the whole rigid body because every particle turns through the same angle. So, unlike linear motion where we need x sub 1, y sub 1, z sub 1, here just one angular coordinate is enough to track the motion. Now, just as we have velocity and acceleration in straight line motion, we define them here. Angular velocity, omega, equals d theta by dt. It tells us how fast the angle is changing. If omega itself changes with time, we define angular acceleration, alpha, equal to d omega by dt. For uniform angular acceleration, alpha is constant, just like constant linear acceleration in straight motion. Let's compare the two words, translation and rotation. Linear displacement x corresponds to angular displacement theta. Linear velocity v corresponds to angular velocity omega. Linear acceleration corresponds to angular acceleration alpha. This analogy is powerful. It means every kinematic idea we know in straight line motion has a rotational twin. That sets the stage for deriving equations of motion in rotation. Start with alpha equal to d omega by dt. For constant alpha, integrate over time. That gives omega equals omega naught plus alpha t. It's the rotational version of v equals v naught plus at. So under constant angular acceleration, angular velocity grows linearly with time. Next, use the definition omega equals d theta by dt. Substitute omega from the first equation and integrate again. This leads to theta equals theta naught plus omega naught t plus half alpha t squared. That's equation 6.37. It mirrors x equals x naught plus v naught t plus half at squared. Notice how the quadratic time term appears in both, capturing accelerated motion. Now let's connect angular velocity directly with displacement. Eliminate time between the first and second equations. The result is omega squared equals omega naught squared plus 2 alpha times open bracket theta minus theta naught close bracket. That's equation 6.38. It's the angular analog of v squared equals v naught squared plus 2 times open bracket x minus x naught close bracket. This equation is especially useful when time is not given in the problem. Let's solve a practical example. A motor wheel speeds up from 1200 revolutions per minute to 3120 revolutions per minute in 16 seconds. Step 1. Convert to radians per second. Omega naught equals 40 pi, omega equals 104 pi. Step 2. Angular acceleration alpha equals omega minus omega naught divided by time. Substituting values, we get 4 pi radians per second squared. Step 3. Angular displacement equals omega naught t plus half alpha t squared. That equals 40 pi times 16 plus half times 4 pi times 16 squared, which simplifies to 1152 pi radians. Step 4. Convert to revolutions by dividing by 2 pi. The result is 576 revolutions. So, the wheel's angular acceleration is 4 pi, and in those 16 seconds, it completes 576 revolutions. A perfect demonstration of the equations we derived. So to sum up, kinematics of rotational motion mirrors linear kinematics. Angular displacement theta, angular velocity omega, and angular acceleration alpha play roles exactly like x, v, and in translation. With constant angular acceleration, the three equations omega equals omega naught plus alpha t. Theta equals theta naught plus omega naught t plus half alpha t squared, and omega squared equals omega naught squared plus 2 alpha times open bracket theta minus theta naught close bracket fully describe the motion. These equations make it easy to analyze fans, wheels, gears, and motors wherever rotation about a fixed axis occurs.